Hello, you're welcome back. All right, so here in this video, we are going to resolve complex capacitor circuit or capacitor connection, okay, which I told you is series parallel connection. Now, in exams, you will see something, okay, you see a network like this. To You'll be asked to find the equivalent capacitance of this network. Now, I have two network. Okay, let me call this one, and of course two. This is two. So the question is, okay, find the equivalent capacitance of this network, or the equivalent capacitance between point A and B. All right, so between point A and B, you have to resolve all these capacitors to get an equivalent capacitance. All right, so now the question is, how do you do that, seeing that this is actually a complex network? The very first thing you need to do is to find out the capacitors that are connected in series and the one that are connected in parallel. Okay, you need to be able to get to resolve the series connection and of course the parallel connection. Now let's start with this number one. Now, what is the series connection? As you can see, the very first branch, of course, there are between point A lies three branch, as you can see. Okay, and I told you that every capacitor connected in branches, okay, are all in parallel. All right, so let's say this is branch one, and this is branch two, and this is branch three. Okay, now in branch three, I have three capacitors connected in series, so I have to resolve it as one. Okay, so if I should redraw this branch, redraw this capacitor, because if I want to solve it, once I resolve one branch, okay, I can redraw the equivalent. So now let me use C1. Let me use C1 to represent the first. Okay, what's the, okay, this third branch. Okay, let me use C3 to represent the third branch. So I will now simply say 1 over C3. Okay, is it going to be equal to 1 all over 2 plus 1 all over 2, then plus 1 all over 2. Okay, of course, using LCM to work on this. For series connection, we've done this before. So C3 now is going to be equal to 12 over 3. I've done this before. 12 over 3 microfarad. So which simply means that if I should redraw this circuit, let me take this one down. Having resolved the third branch, okay, if I should draw the circuit, I can simply say that, okay, for this third branch, the capacitance, the equivalent capacitance is 12 over 3 microfarad. Okay, all right, let me do that one. Let me do that one. I've resolved this branch, so I can just use one single capacitor to represent the equivalent, and the equivalent is 12 over 3. So I'll just do that. One capacitor represent the equivalent, and I have another one, second branch, and of course the first branch. Okay, so all these three branches are all in parallel. So this terminal A and this terminal B. So I've already resolved the third branch, which gives me 2 all over 3 microfarad. So of course this is 2 microfarad and this 2 microfarad. So everything now, okay, everything now are in parallel, and you know how to resolve parallel capacity. Okay, that's gonna be C total, of course, is gonna be C1 plus C2, then plus C3. So that's gonna be equal to 2 all over 3 plus 2, then plus 2, which of course is 2 all over 3 plus 4. Okay, so resolving that using LCM is 3. It's all over 1. 3 divided by 3 is 1. 1 times 2 is 2. Of course, 3 divided by 1 is 1. 3 divided by 1 is 3. 3 times 4 is 12. So everything now becomes 14 all over 12 all over 3. Okay, so you can use calculator, do that with calculator. All right, 14 all over 3. What do we have? That's 4.7 approximately. So that means the total capacitance or the equivalent capacitance of this entire network is, okay, 4.7 microfarad. So as simple as that. Let's go to this. Now let's analyze this. Okay, between point A and point B, you discover that there are, okay, parallel connected capacitors, all right, in the same line. Two parallel connectors of capacitors. Let me call this parallel 1, this is parallel 2, and this is a single capacitor. So both the parallel capacitors, okay, let me call this C1, let me call this C2, and I call this C3, okay, because the whole of these are in parallel, the whole of these are in parallel, this is a single capacitor. All of it are connected in series, right? So this single capacitor plus this parallel connection plus this parallel connection are connected in series. So what will I have to do first before I find the total or the equivalent? I'll have to resolve the parallel connection first. Okay, so let's start with C2. C2 parallel connection, of course, I'll add. That's 2 plus 2, which of course is 4 microfarad. Right? Then C3. 2 plus 2 plus 2. Okay, 6 microfarad. So I'm evaluating everything. I'm gonna have 1 all over CT. For that's gonna 1 all over C1. That's 1 all over 1 plus 1 all over C2. 1 all over 4 plus 1 all over 6. Okay, applying LCM. The LCM of the denominator is 12. 12 divided by 1 is 12. 12 times 1 is 12. Then of course plus 12 divided by 4, that's 3. 3 times 1 is 3. And 12 divided by 6 is 2. 2 times 1 is 2. So doing all this, now I'm going to have 1 all over CT is going to be equal to 12. This 12 plus 5, that's 17, okay? If I'm not mistaken. Yeah, 17. 17 all over 12. So now remember what you're looking for is total capacitance CT. So that's going to be 12 all over 17. So let's do that with calculator. 12 all over 17. What do I have? 0.7 approximately. 0.7 microfarad. So it's just for you to know the connection, then you can resolve it. All right, I hope that is well understood. I will still solve more questions on this. All right, but let's actually conclude by looking at the energy stored by a capacitor. Okay, energy. Now a capacitor stores charge, and if a capacitor stores charge, okay, that charge is stores can actually, the capacitor can do work, okay, when that capacitor is being discharged. Okay, so because capacitor can do work, then that capacitor actually possesses energy by storing charge. Okay, so that's what you're going to be looking at in the next video. All right, see you in the next video. Thank you very much.